So this work is about self-concordant Schrödinger operators. So I personally work on quantum algorithms. So this is about quantum algorithms, but what we're using is we're using self-concordance, which is from convex optimization. Has anybody heard about self-concordance? Have you seen like convex optimization? A little bit continuous optimization? A little bit, okay. And then there's Schrödinger operators, right? So the maths of Schrödinger operators. So I'm an expert in neither of these areas. So you know, let's take it slow. I'm also learning a lot about this. So we combine these two tools a little bit to get new quantum algorithms. That's kind of roughly the contribution. Right, so a small disclaimer, so all the bad handwriting is completely caused by the train I was on when I wrote this. Okay. So rough outline, I'll introduce classical optimization, convex optimization, right? So first order and second order classical convex optimization, right? So and we'll take it slow, and then I'm going to introduce something that I'd like to argue sort of a quantum version of first order and second order convex optimization. And then to sort of make the case for that, like we'll look into applications in interior point methods, which again the classical tools that I'll introduce, and then how we obtain quantum versions of that, right? And that with like a new quantum interior point method. Good. So let's start with classical optimization, convex optimization, more precisely. So we'll talk about the convex smooth functions f, picking a sort of n-dimensional argument, giving you a real number. And we typically just want to optimize this function, right? So we want to find the minimizer of that function, or we want to find x such that f of x is close to like sort of its moment. So what's sort of first algorithm you think about for solving such a convex optimization problem? It's probably gradient descent, right? So what you do in gradient descent is you take some initial point, right? Just take any x, and you compute the gradient of the function, and you're just gonna sort of move in the opposite direction. Here, downhill section. So for the gradients here, that's what we call first order information, right? It requires like first order derivatives. And so what we do is we just take a step in that direction, and there's some parameter eta, which is kind of important. Tells you like, you know, how far in that direction am I going to move, and then you repeat that. Okay, again with the ultimate purpose of sort of minimizing, like finding a minimizer, approximate minimizer of f. So throughout this talk, what's going to be very the guiding example always is quadratic functions. Okay, so this is going to be like a critical example for first order optimization, second order optimization, but also for first order and second order quantum optimization. Okay, so let's sort of make sure we get this picture right. So the simplest basically, like a typical example is a quadratic function, right? It's sort of a nice convex function. Performed like 1/2 x transpose ax, where A is a positive definite matrix. All right, so f is not going to be just convex; it's going to be strongly convex for everywhere. And then the gradient of f is just A times x. Strongly convex means that like a constant function is convex, but not strongly convex. Right? The gradient, we want the gradient to be non-zero. Yeah. That just makes it a bit simple. Means that you have like a unique minimizer and everything like that. Any other questions so far?
For quadratic, the gradient is 0 at some point.
Yeah, at some point, yes.
Also, yeah, almost everywhere, not every.
Right, exactly. Yeah. Okay. Good.
I have a dumb question.
Yeah, sure.
It's not fully directly related, but intuitively, a derivative is like looking at adjacent points, and like the second order is looking at slightly farther points, intuitively with the status and the rate of change.
Sure. Yeah.
Is it the case? I don't know. I forgot my answer. So, is it the case that if I give you all the derivatives of a continuous like well-behaved function,
Yeah.
Like all higher order derivatives are negative point. Does it completely specify the function?
Yes, and it's an analytic function. Yes. So I guess it can be I'm sorry, finite set, right?
It can be.
It's not necessarily finite, right?
Yeah, it's
because
not
the function analytic, I guess it's completely determined by the state of series. Yeah. Yeah. You can assume that if you want. Okay, good. So we take this quadratic function. It's kind of easy, and we can analyze what this gradient descent does, basically. Make it even simpler. Let's look at one dimension. Okay, so fx is just 1/2 ax squared. F prime is ax. Our gradient descent looks a bit like that, right? We're just going to take x minus eta times ax. Okay. Now, we don't want to overshoot, right? We don't want to jump over the minimizer. So it means that eta cannot be larger than 1 over a. And in fact, we want to be close to the minimizer, so we want to take something like eta approximately 1 over a. Okay. And one thing that there's always sort of a step size that works pretty well that brings us close to the minimizer, even in one step. Okay. But this sort of dramatically changes if we go to higher dimensions. Again, it's like a key point, so I want to stress this a lot. So let's take a two-dimensional setting where we can even assume it's diagonal because a equals lambda 1 and lambda 2. And then the level sets of this function, right? If I over the sub-level sets, so we take all the x such that f of x with the most 1, let's say, looks a bit like this ellipse, right? With x of length 1 over lambda 1 and 1 over lambda 2. Okay. So we don't have such a picture in 1D, right? In 1D we just have like one interval. In 2D we sort of have this sort of shape all of a sudden, and the shape can be nice and round, but it can also be very ugly and stretched, right? But if you do gradient descent in this case, we've got to be subtracting a times x, okay? So if you have a very sort of stretched out shape like that, then the gradient can look a lot like that. It sort of generally points in the right direction, right? In both coordinates you would be improving, but in order not to overshoot, you actually to take a very short step length, right? The step size, theta, will be bound by 1 over lambda 1, where lambda 1 is the largest a value. Okay, so we don't want to take eta larger than that, or we're sort of grossly overshooting. That means that we can only take sort of tiny steps, but we need to cross a large distance in that direction, right? So if you just sort of put these two things together, and the number of steps that you would need, so back of the envelope would be something like lambda 1 over lambda 2, right? We need to cross the distance of like 1 over lambda 2, and our step size is 1 over lambda 1, okay? The number of steps is something like lambda 1 over lambda 2. And this is precisely what we call the condition number of the A matrix, right? This condition number sort of pops up very naturally here. And if you do quantum algorithms, then you sort of always shrivel a bit when you hear condition, because that's always like the thing that we don't like in quantum algorithms. Right, in quantum linear systems, solving stuff like that, you always have to be careful about this condition because it pops up and we don't like it. Okay? So it pops up in this super simple example here, in first order classical optimization.
I have a good question, because I'm not fully following.
Okay, yes.
So the question is that can we not somehow have the step size be different along the direction?
Well, no, right? So okay, so this is the primitive, right? This is the algorithm we're running, right? So we're gonna take a certain direction of the gradient, so that direction is fixed. If I'm gonna change direction, then sure I can always find one. But yeah. But I mean, this is going the right direction, right? Like you feel like, okay, maybe the gradient is not the right direction. Okay, actually there is a better direction, but this better direction requires more information about your function. If you're just using gradient information, it seems you get this sort of condition number dependence, and that's sort of unavoidable. You can get this down to like square root kappa if you use things like accelerated gradient descent with Nesterov methods. But still you're going to get this condition number. Now there is, however, a very nice way of sort of getting around it, and I guess you're sort of pointing in that direction. So second order optimization, sort of a well-studied area, and this is sort of an approach that fixes that problem. Okay. So here we're going to assume we have some smooth, strongly convex function f. So in particular, f has the Hessian that's positive definite. Okay. So h of x, my Hessian is positive definite. Move this. And then using information both from the Hessian and the gradient. So now I'm sort of giving you also this Hessian in every point x, right? You can evaluate the Hessian as well. So that's second order information. If you're on top of this first order information, also getting second order information, and we can do this thing, which is called the Newton step. And that's kind of a smarter optimization step. Like you could say that the gradient descent sort of looks at the first order approximation of your function, and based on that, it decides where to go. This looks at the second order approximation, and then that's sort of the best guess that you have. And then I guess again, there's step size here.
It's the inverse of the Hessian.
That's right. That's right. Yeah. So let's see why this makes a lot of sense. If we take again a quadratic function f, then our gradient is ax, and our Hessian is just this A matrix. Okay. So what we see is if you take a Newton step out, then you're sort of correcting for this potentially very ill conditioned matrix A by your Hessian. Okay, so this extra Hessian information is precisely capturing sort of ill condition. So then you can correct for it. Okay, and then you're getting at something like x minus theta x, which is what you got, like essentially the 1D case first order optimization. And we see that I sort of try to optimize this function without having complexity depends on condition numbers. Okay, good. That's kind of an important takeaway. So, like if you first order optimization, you get this condition number showing up, right? If your sort of problem is sort of ill-conditioned, ill-shaped, then that shows up. Second order optimization then gives you a way around that. What's like the sort of on a broader level, what's a key property of second order optimization is scale invariance. So if you imagine, you're optimizing a function, then right, and it's sort of ill-shaped, what you could try to do is sort of reparameterize your coordinates, right? So choose different coordinates, like a linear transformation, so that your function is sort of all of a sudden nicely shaped. Right? There exists a different set of coordinates, so that your condition number is okay, right? So if you would do that, right, take y to be b times x, you take this new function g of y, then the key property of this Newton step is that taking a Newton step in these u coordinates, it's actually you're sort of running the same algorithm, right? So your algorithm doesn't depend on the coordinates that you chose. And since this condition number is tied to the coordinates that you chose, sort of the runtime of your algorithm won't depend on the coordinates that you chose, and so these condition numbers won't show up.
So what happens if you choose the right coordinate and run the first order? Is it also more?
No, your gradient does depend on the choice of coordinates. That's a problem.
But if you first correct the problem.
Yeah, exactly. So this is something you can do, right? You can first correct and then run a gradient. But then you need the point is this correction is the second order info.
Okay.
Right?
So it's equivalent to, or is it still different? Yeah.
So it's equivalent in this sort of simple setting where you have one global transformation that makes your problem well conditioned, right? So for quadratics, exists simple transformation, but more generally, this Hessian might change, and then your new step is sort of taking into account everywhere locally works, right? There might not exist a global. Exactly. Yeah. But that's sort of a key point. So when we do quadratics, your Hessian doesn't change, and that makes a lot of things easier. So it demonstrates stuff, but you're really making it a bit too simple as well. But anyway, so that's for quadratics, right? So it's actually, we can sort of elaborate a little bit, what if we take a more general convex function? Yes.
Is A always inverted?
Yeah, so I'm assuming that A is positive definite because I'm assuming a strongly convex function, right? But the key point is if your function would be, let's say, quadratic in one coordinate and let's say flat in the other coordinate, then this Hessian blows up, right? And the key point is that your Newton step would like to take infinitely long steps somehow, and so things don't work so well. So we're assuming that. Okay, good. So turning to more general complex functions, what can we say? Okay, so you sort of argued that if there's this global transformation that turns your problem into a nicer problem, then you're good, right? But then you might as well do, just sort of learn the hashing in one point and rescale your entire problem and then do classically first order gradient descent. If you get a more general convex function f, then I guess you could ask something like, what if my global, like Hessian everywhere, is sort of close to one fixed Hessian, right? You could ask something like that. And sure that would work as well. Now, what self-concordance tells you, so this is sort of a weaker notion. It tells you that your Hessian doesn't have to be like globally close to some fixed Hessian, but your Hessian has to be stable. What does that mean? It means that, right, I'm going to take these sort of smallish steps, right? So if I do a Newton step like that, then I, like, over sort of the distance that I take that step, I want my Hessian to not change too much. So globally it can change, but with respect to these Newton steps, I want my Hessian to be somewhat stable. So you can formalize that. So if I take some perturbation delta, which is small, so let me explain this more in a second. But think about it, there's some small perturbation, then I want my Hessian at x plus delta to be spectrally close to the Hessian at x. Okay, so you can just think about it as close. Like your Hessian that should be stable, right? Like a small change in coordinates should result in a small change.
This does not depend on the coordinate.
Whether your Hessian is stable, so it doesn't depend on the coordinates because I'm taking this one, right? So if I would just take, let's say, Euclidean norm, then that would depend on coordinates. Now I'm taking this local norm, which is essentially sort of the inner product induced by taking the Hessian. But if you take this inner, but that's a great question. So if you take this inner product, then this is kind of scale invariant property.
That's important.
Yeah, that's key. Exactly. So this norm, you really want to think about it as like, if you have a very ill condition, like in some coordinate, like some trivial coordinates, very ill condition, then taking like a perturbation in that direction can be large in the perturbation in that direction, right? So just it sort of weighs different directions correctly. So okay, in this sort of scale invariant norm, if I take a small perturbation, I want my Hessian to also be stable. Okay, so this notion of self-concordance sort of intuitively captures, like, we want to have behavior that's similar to a quadratic, right? To this quadratic function, and this notion captures that.
I'm sorry, so how do you know that's the right norm, even other than the fact that it preserves the coordinates? I mean, it's preserved under coordinates. Other things could also do it, right? Like, so how did you figure that this is the right?
So, okay, we don't introduce this, right? Like this.
Say, actually, how does one figure? I don't know if it's anything deep, I don't know. Like, if I was thinking about it, I wouldn't think of
But won't that be determining that it's unity of the space where
Yeah.
who is studying, for example, on this aspect?
Okay.
Right. So I'll talk a lot more about that. So thanks for already mentioning that. Right. So this is a very natural metric for optimization problems. It's a very natural metric. It'll show up a lot.
Is it the same stuff they use in like Riemannian stuff?
So we're going to do Riemannian stuff. We're going to do Riemannian stuff in a couple of slides, and that's going to be exactly the picture.
Yes.
No, so okay, we did introduce this. So this was introduced by 94 by Nesterov and Ibrovskis. This was a big work. And what they wanted to do, they wanted to somehow capture like what is the property that we need of our function f for Newton's method to work well, right? It's sort of a nice property that and they show that if your function satisfies this function self-concordance, okay, then there's the technicality, like assume for a second that x0 is sufficiently close to x star. So I didn't put this, but then my co-author said, okay, it's blasphemous, you have to put it, but it's really essentially technicality. So if you're sufficiently close to your optimizer, then what you get is that under Newton's method, you get this sort of doubly exponential decay towards the minimum. So that's kind of shy, right? Like if you look at quadratics, then you could get sort of like exact convergence by taking your parameter, your eta to be 1. Right? So clearly, Newton's step can contract very well. So they made this more complex. For this bigger class of self-concordant functions, you're sort of contracting towards the minimizer, and your function value decreases. Your gap decreases as 1/2 to the k.
And then what are some like nice examples of such self-concordant functions other than quadratic figures?
So that's a good question.
Is it a huge family? I think of it as like covering almost everything I would care about.
No, definitely not. So I think self-concordant is kind of a strong notion because it asks that this hashing is stable like everywhere, and typically we just want it to be like stable around the minimizers. But the key point is that the way this is typically used is in interior point methods, which I'll talk about more. And there you just imagine that like there you do have this huge family where you take some convex domain, and actually I'll talk about that more, but please ask. The thing I just wanted to add here, like the main point is that this convergence is independent of any condition, or let's say even independent of the dimension. So I think this wraps up my slides on classical first order and second order optimization. So
What is K?
K is the number of iterations. Yeah, I didn't introduce it formally here, but xk would be if I take k new step starting at x0. Are there any other questions?
So then, in these cases, the classical complexity is also really good.
Yeah, that's right. Yeah. If you have this first order gradient and hashing information, then that works pretty well.
These are local objects. It should be easy.
Well, what's easy, right? Okay, we're doing convex optimization, so that's already easy in some sense.
Yeah.
Right. But then you really care about like sort of. So this is dimension independent, but computing at first and second order information is not dimension, right? So and then you have to invert this hashing. So you might be looking at like n to the omega, like matrix multiplication pattern and so on. Then people start looking at approximate gradients and so on, stochastic gradients, stuff like that. There's still a lot of wiggle, but maybe it's important to point out that indeed like this entire area is convex optimization, and that's already sort of the class of problems that we can solve in polynomial time. Question is a bit more about what polynomial. Okay, good. Then maybe I'll turn to quantum. Right, so first order quantum optimization. So what we've seen in the literature, and I've worked on that, and other people have worked on that, is quantum algorithms for computing the gradient faster, or approximating this hashing faster, things like that. Yes.
So going on, so in the previous slide, the result that you show is basically saying that it doesn't depend on the problem size at all. That's the rate of convergence is fundamental to the problem.
That's right. Yeah.
And so you're probably trying to accomplish something similar with bigger class of problems.
I think it's up for debate what we're doing. So I think we're sort of introducing a sort of natural quantum notion of these problems and so on. I don't think at this point we're trying to we're trying to speed up like maybe this is sort of like building block for that, but no, we sort of I'll try to explain a little bit why we do what we do. Whereas you have quantum algorithms for like implementing classical optimization faster, right? So speeding up computation of the gradient of the hashing and so on. So what we do, we do something different. We sort of introduce a very natural quantum object that we interpret as a sort of quantum version of classical first order optimization. Okay, so this is nothing new, right? So we're just looking at the Schrödinger operator H, which is minus 1/2 the Laplacian plus the function f. Okay, this is just the usual Schrödinger operator. We're going to assume that f is a smooth and convex function here, and let's not go into domain issues, but let's assume that at least all compactly supported smooth functions are in the domain of H. Okay. You can always think about compactly supported functions. Good. So I want to sort of make a case that this is like the quantum version of first order classical optimization. with respect to the function. So this is the same function f as before, except that now we're looking at a quantum operator here. All right, so let's sort of dig into this operator a bit and see what we can say about it. So if f is non-negative, which I can always achieve by sort of shifting it if I want, and as x goes to infinity, as x goes to infinity, right? So it sort of grows, right? So it's somewhat like like any strongly convex function would satisfy this. Then what we get is that H has a discrete and non-negative. Okay, so it has a discrete set of eigenvalues. They're bounded from below, like they're being bounded from below by 0. And that's already something not true. Okay, like if you first don't have this F, you get a continuous spectrum and so on. So we really want to have sort of confining potential that gives us a discrete non-negative spectrum. Okay, that's nice. That's nice because that means that we can define things such as the ground state, like the ground state energy, and most importantly, you can define what the spectral gap is of this operator, right? Which is going to be the gap between the smallest eigenvalue, the ground state energy, and the first excited energy. Okay? Spectral gap is also something that's sort of.
But so how do you? So, for instance, here in this case, in your setup, how do you access H?
How do I access it? That's a good question. So, right now, I'm just going to talk about the operator, about the object on itself. And I think, like, if you want to think about like algorithms, I think you want to think about sort of a black box Hamiltonian simulation of H.
And it's already like this F is already in some discretized form appropriately, or you consider it to be continuous.
Let's just do continuous variable. So, okay, so I think this is also something in our paper that we try to sort of make a case for, which is that there's all these beautiful things in continuous space. Like let's try to use, because we all have the reflex, let's discretize this and let's put it in this sort of framework that we have and quantize it like that and so on. But I think we're trying to make a case that we get sort of a beautiful theory if we don't do that. And there's like work to be done there. But so here, like we're just going to assume, like it's a little bit like for convex optimization. I didn't talk about putting a grid on Rn and so on, because then stuff becomes RP again. So let's talk about the continuous version. So for now, I'm just talking about this continuous operator here. It has a spectral gap, and essentially we're interested in that spectral gap. Okay.
So basically, are you going to also implement it on continuous variables? Is that the target, or are you going to discretize it?
No, we don't discretize because we already have a lot of work with continuous stuff, and I think that and this actually narrative that you see in classical algorithms as well, like diffusion models and like a lot of like random walk processes and so on. You sort of there's like one line of work that just looks at the continuous dynamics and tries to understand that, because there like you can use PDE stuff and so on. You can use nice stuff. And then, there's going to be another paper where you sort of do all the work in trying to discretize it and so on. Then you have like numerical integration, sort of an entirely different story again.
What I meant to ask is actually something similar. So even if I'm solving some continuous, like if I'm using floats or whatever on the computer, it's still discretize, right? When I'm running it on the computer.
Well, I mean, isn't like I guess quantum mechanics ultimately is about continuous variable.
Yes, quantum is a little bit different. Right. The discretization that you're doing is like the amplitudes are already inherently continuous, but the degrees of freedom are not continuous. So like we don't have, like, for example, a superposition of floating point.
No, but I think what you say is in mind is really then something as variables.
Like you're having dynamics last Exactly. So so quantum harmonic oscillator. That's against the key example here, right? And maybe this sort of, get your mind at rest a little bit. Like this is supposed to be, a very physical object, right? So we can talk about it. We don't have to talk about qubits. So we can talk about that. And so notice that, it's sort of stupid and simple, but it's again this quadratic, right? So what's the textbook example in convex optimization? It's quadratic. What's the textbook example of like Schrödinger operator is quadratic? It's harmonic oscillator. So we're sort of triggered by that. I think it's part of the motivation. But so there's a quantum harmonic oscillator. I'm not sure like who has seen quantum harmonic oscillator. Almost no one. Okay, that's fine.
Almost everyone.
Almost everyone. You sort of like, okay, like I also always sort of pushed it out of my brain as much as possible, because I also I'm not necessarily a physicist, but in this setting of like classical convex of mind, there's really algorithms, like, then quantum harmonic oscillator, that's where the physics make sort of new appearance, and I don't know, I'm really enchanted by them. So what can we say about it? We know we can exactly sort of diagonalize. We know what the eigenvectors are. We know what the ground state. We know what the energies are. So let me just summarize. So the ground state energy is 1/2 trace of square root of A. If you have now instead of A, take square root of A, and the ground state energy is sort of the sum of the eigenvalues of square root of A. The ground state energy corresponding ground state like a nice Gaussian. Okay, I say this quadratic potential, your ground state is a nice Gaussian. So we understand you have an explicit form for it. And for the spectral gap, the first excited state is just lambda 0 plus the smallest eigenvalue of square root of A. Okay, but you really want to think about this as being essentially like you can sort of split it up into an n-dimensional quantum harmonic oscillator as like n one-dimensional quantum harmonic oscillators. Right, but sort of look at diagonal basis. So we see that the spectral gap is like lambda min square root A, but really we should be, and this is like where things become a little bit fuzzy. So we should be caring here at the ratio of this sort of spectral gap over the smallest eigenvalue, right? Because it's sort of like the energy norm, if you want, right? And then you see that, okay, you get this 1 over n, but again, you get a condition of, right? So you get square root kappa in this case. So we see that, if you would like to optimize the operator, which probably means like prepare the ground state, then, this is going to be tied to the spectral gap complexity of that, right? And the spectral gap shows the condition number. So there's this analogy with first order optimization already in this simple case, quantum harmonic oscillators. So then what we do is we go beyond that, right? And we say, what if you have a more general convex function? Yes.
Sorry. So, is there like a simple or the statement that you have over there that H has discrete marking spectrum?
Oh, for this one?
Yeah, because I only studied like the one for quadratic, but apparently it's much more general statement. Right? You're saying it's true even if there's any strongly convex, no smooth convex.
What you need is that F. It's a confining potential. Like it sort of needs to be, you want to have nicely L2 eigenvectors. That's sort of the key point. Your eigenvectors have to be confined. They have to be integrable, right? Which is the key difference. If you just take the Laplacian and sort of get free emotions but not integrable. I don't think I have a
sequence thing. Is it standard in the textbook?
Yeah. So this is textbook material. Like
I think this comes from the Fourier series, right? On momentum traffics, the conjugate variable P becomes discrete. So
I don't know. I'll ask you.
And that's why P particle has to talk about X, and so P, spectrum is also.
So
particle in a box, harmonic oscillator, all this problem, variable stop, if the spectrum is discrete. Because you get the series. Otherwise, it's
right. Okay. I have this next
So it depends on H, right? It depends on H. Yeah. You're saying that's what is potential.
Yeah, as we confine it, because I guess if you have like sort of a quadratic on one side, but then you have like sort of outrun, or like you can sort of your vacancies can sort of flow out in one direction. That's that.
Yeah, like what you're doing to your free particle. Free particle has continuous spectrum.
Yeah, exactly. You sort of wanted to. Right. Okay.
For which it is discretized but not low bounded by 0.
Well,
Or is it the same?
Okay, it has to be bounded from.
Somewhere.
No, I guess it doesn't have to be bounded. I guess
It can just be discretized.
it can be this, but I guess if that's not bounded from below, you might still have this free spectrum, but that doesn't bound from below.
Like if the energy is like somehow going to minus infinity in between, mining you might have. Okay. Just getting a handle. So.
No, but this is great. This is all kind of like interesting stuff that I'm also learning about. So So it's a bit like sort of dusty textbook stuff, but it's nice to sort of get a new fresh look on this, like connecting into quantum algorithms and so on. So, sort of try to like motivate people to look at this more. Good. So okay, let's move away from harmonic oscillator. What about general convex function stuff? Okay. So, kind of like, you do some general convex function f, and we're assuming f is nice and smooth. And you have minimizer at 0, the gradient is hence 0 in the origin. Have a Hessian A. Okay, so it's quadratic approximation of f, which sort of works close to the minimizer, right? So what we do is we do a non-asymptotic semi-classical analysis of this Schrödinger operator. Okay, so I'm going to explain these words. We'll start by semi-classical analysis. So this is again sort of this like old textbook stuff, right? What it's telling you is that instead of taking your original operator H, like let's add this extra parameter gamma squared. Okay, so we're going to add this extra parameter gamma squared, and we're going to make it large. Because the idea is you have these sort of two terms. If you think about like constraint satisfaction or something, you want to sort of like satisfy both terms, like in equal terms. But if you're making this one much bigger, then you have to like take that one much more into account. And so somehow your ground state will be like concentrated close to the minimizer more and more as you sort of like pump up gamma. So much that if you take gamma big enough, then your Hamilton is actually nicely approximated by just taking a quadratic approximation of f. Okay, because we know close to the minimizer, f is essentially this thing, but then this thing is just a quantum harmonic oscillator. So we know what the spectrum is of H0 gamma. Good. So slightly more precisely, this approximation holds when gamma is sufficiently large. And also for like low energies, let's say for the ground state energy and for the first excited state energy. Okay, so these are the spectral properties that we care about. Okay, good. So this stuff was around, right? Semi-classical analysis has been around for I think 100 years in physics and 50 years in maths. But we're doing computer science, right? So we have to do something else here. The problem is that what these papers prove are statements of the following form. If I give you a fixed f, then I'm going to look at the limit for gamma very large. And for every f, there exists a gamma sufficiently large so that this holds. Now that's an asymptotic statement that's essentially useless in a computer science context because they're not thinking about f as some sort of input of a problem, like we do, right? So what we want to do is we want to do a non-asymptotic analysis. So we want to prove this kind of statement uniform over a family of functions, right? So we don't want to prove the statement just for one function. We want to say that, okay, for any function in this family, this fact applies, okay? This is my classical analysis applies, and hence you can sort of, use like design an algorithm for this that works with full family of functions. Okay, so I want to sort of emphasize it because it took me a long while to sort of find the right words also to make, what do we mean by this non-asymptotic, right? So again, in algorithm computer science, you want to sort of consider the family of inputs and you want your algorithms to work uniformly over that family.
So gamma would exist for the entire family.
That's right. That's right. So that's precisely what we show. So we show that if f is self-concordant, so we show that this self-concordance, which is sort of key in classical optimization, is also extremely useful tool in, let's say, quantum optimizations. If f is self-concordant, and we do need that, so it doesn't work for arbitrary convex, because this is what you would call a family, right? So assuming that f is self-concordant. And we take gamma. So is it like a uniform lower bound? Like gamma has to be at least some polynomial in n, let's say the condition number of the Hessian. Okay. Then this further restricts the family, like we're saying, okay, any function is self-concordant and has this condition number. Then we can take gamma so big, and then this Schrödinger operator has this grounded energy and this spectrum.
The next term in the energies is like the gap and the energy is all for gamma squared.
Sorry?
So the energy, the ground energy now
Yes.
Which is approximately gamma times this, so it's linear in gamma.
Yes.
The next term is order gamma squared.
No. Because this is a spectral gap, right? So essentially,
Sorry, 1 over gamma. 1 over gamma.
your entire spectrums. Yeah, you get the molecular spectrum times gamma, right? So
And there must be some error, right? Like in this.
yeah. So okay, this is not just bad handwriting. This is actually sort of approximately equal. Okay, so you get something like a lower order correction in gamma, like plus order gamma to the 4 over 5 or something. But taking gamma that big, then we get sort of the spectral gap that we want. Okay, so this is what we prove.
Yeah, it's a big number or a small number?
Well, it's kind of big, right? Well, so it's polynomial in n, which is sort of fine, but then it has to be polynomial in these condition numbers. So
No, why I'm asking is that the correction should be in like 1 by gamma.
no,
The correction be gamma 4. If gamma is big, gamma 4 is going to dominate. Am I missing something?
so we have the gamma here.
Gamma to the power something.
Yeah, gamma is something plus or gamma 5. So gamma is big, right? Gamma is big. So we get something big plus something not as big, but also big, but not as big, right? Gamma to the 4 over 5 is little of gamma, right? We could alternatively write this as gamma times something plus little of 1. Yeah. Plus order 1 over gamma.
Okay, I didn't put the dimension.
Yeah. No, so clearly, like, and this is already like a bit sort of the meta discussion. We're making this gamma big, and then we get a gap that scales with gamma, and so clearly not just the gap is what matters. We somehow have to pay a price for making this gamma to be very big, but we can talk more about that later. But these are the mathematical facts.
This probably is difficult to derive, right? Since
To prove this, yeah, it's a bit of a hassle, but the blueprint is there. So there are these sort of Sandy Barry Simon that has a very nice paper on that. He has a lot of nice stuff that we still sort of need to make non-asymptotic. I guess. So you need to find the right family for which you can make all the constants explicit, which is what we do. So that's first order, and this like should really parallel somehow first order classical optimization, right? If it's condition number showing up, and we get polynomials in the dimension. So a lot more work goes into turning to what we call like second order quantum optimization, right? So we use gradients in first order quantum optimization.
For the second one, for the first one, do you think that there should be a bigger family for which you could derive such a result, or you think it's sort of?
Yeah. Yes. I mean, the result is not going to be you're well approximated by quantum harmonic oscillators, but just that you have a nice gap and so if you have a convex function. Yeah, there should be like other arguments as well. Okay, so turning to second order quantum optimization, what could that be, right? So what we did in the classical setting is we sort of replaced this gradient by this rescaled gradient, okay? The gradient multiplied with the inverse Hessian. If you squint at it the right way, and I guess if already some people mentioned Riemannian manifolds, I guess it's even easier to argue that you can think about this as the Riemannian gradient. Okay, so I'm going to go over this. Like, if you're not very familiar with Riemannian manifolds, then we're at least two in the room. So you can think about this as the Riemannian gradient. What does that mean? So we can define a Riemannian manifold G, which is you take the original Rn state space and you introduce a metric induced by the Hessian locally. So intuitively, how do you want to think about this? I think this is insightful. So the local volume element, right? If I'm going to do integration and so on, if I just have Euclidean space, I can just get sort of like the Vega metric dx, right? But now I'm going to rescale every volume element by the square root of the determinant of h of x. What does that mean? It means that if I'm sort of a very curved part, then I'm going to sort of stretch that volume. Okay. And so that's what we call a Hessian manifold. Right? So it's a manifold. So it's sort of like replace Euclidean space by a space that takes into account the sort of local curvature. Right? And then it turns out that the new descent is really just doing gradient descent in that space. So if we phrase it like that.
So the term is it like because you're taking the product of all line values? That's kind of making point.
Yeah, that's it. That's right. Yeah. But I guess you could think about like being a diagonal basis. Okay. Good.
H is always mission.
H is always remission. Yeah, that's a Hessian. So, like again, insightful. Okay, maybe I'll talk about the quadratic case again, obviously, and then it's sort of nice and clean. It'll suffice to think about that. But anyway, once we define this Hessian manifold, we can define the Schrödinger operator on this Hessian manifold. Okay, so this is what we call sort of the second order Schrödinger operator. Essentially the same Schrödinger operator, right? You take care of like -1/2 Laplacian plus f, except that now this Laplacian takes derivatives with respect to manifold. Okay, so this is what you call the Laplace-Beltrami operator on this Hessian manifold.
Does it have to do with the trying to extend of is like quantum gravity stuff?
I hope not. No, maybe no. I don't like. I mean, this is just PDEs for like it's just differential equations for us, right? Like it's
but like is it like something specific for nature? Specific
to have that this exists. This how?
Yeah, does it describe something in the
I guess maybe other people know better.
The square root of derivative comes from the Jacobian. Because you want to, you are basically translating from the Cartesian coordinate to curved coordinate system. So that's it. So beyond that, it's of course it's very similar to what the relativistic people will use as the general metric and how do they define this least distance and all that. So it is very similar.
So this is something that I don't know. Like I guess yeah, you could maybe think about our space being curved and you define quantum mechanics, and maybe it's the natural object outside of that. So, okay, we define it as in this context we define it. It's probably been studied in very different contexts. So this is Laplace-Beltrami operator, which roughly you can think about as sort of replacing your gradient by this sort of rescale gradient. Yes.
Can you please explain the Hessian manifold?
Right. So you sort of imagine you still have the same space, so it's still Rn, except you introduce a new metric on it, which tells that the distance between the 2 points is not the Euclidean distance, but you have to sort of take a distance along some geodesic, and really you want to think about it as if you have a sort of very ill-conditioned potential or something like that, and if 2 points are far apart in that direction, then you're going to charge that less than if they're far apart in that direction, right? It relates to this norm induced by the Hessian, right? Sort of, like x, h, y, something like that, right? Sort of. So maybe it'll be easier if we just look at the quadratic case, because that sort of, and that's really what it's all about at this stage. So if you can take a quadratic function, you get sort of a flat manifold. So the only thing what happens is that your inner product now is rescaled by this Hessian. So you can really think about that as sort of implicitly doing the coordinate transformation that we wanted to do all along, right? Based on the Hessian, right? And if I kind of like write down this operator explicitly in this case, and then this Laplace-Beltrami operator, it's really just this thing. So the gradient transpose a inverse gradient. But what you have here is really just the usual constellation. Right? It's really just the usual. Like, if you take different coordinates, so we care about spectrum and so on, right? Eigenvalues, and eigenvalues don't depend on the choice of coordinates. So if I'm saying, okay, this operator is this one in different coordinates, then actually that's the operator that we're sort of dealing with. We don't really care about the coordinates that we choose.
No, I think got lost because you can scale things, right? And the eigenvalue will scale. So you would have some subset of transformation that might not share. Right. Linear assumption.
No, I don't agree.
That has already been done.
Right.
So we have to figure something else. So I think this says is that this is just like your standard. Yeah, you can just use standard linear system. Like this one, but just choosing these different coordinates.
So-
in this case, it's a scale.
Yeah, in the scale,
why
in general, it's not a scale. It's very similar to the discussion on first and second order classical optimization. For the quadratic case, it's Riemannian manifold just does sort of a global rescaling, and then it turns out that your second order Schrödinger operator is essentially equivalent to the normal quantum harmonic oscillator. Okay, and from that operator, we know there's no condition numbers there, right? So this sort of harmonic approximation found like a sort of quadratic approximation. I guess it's not even an approximation. The quadratic case in the second order setting gives you the normal quantum harmonic oscillator, right? And you contrast that with the Euclidean setting where you got this potentially ill-conditioned harmonic oscillator. Okay, so in particular, what you have is that again this operator. You can forget about that. The conclusion is this operator. If I replace my Laplacian by this Laplace-Beltrami operator, then all of a sudden my spectral gap is just one, the constant, independent of the hash f, independent of the coordinates, and then there's this transit energy 100 times n. Yes.
In the first line, you have these two terms, right? It's half of delta transpose and then plus half of x transpose. So on the right, it's like a number.
This is a number, right? Yes.
And then what on the left, it's an operator.
Yes, but this is like a diagonal operator if you want. I'm writing, but you want to think about this x like x hat, I guess. It's sort of the position operator.
So x is the argumentary parts to this.
No, so this is an operator you apply on a function, right?
Okay, so it depends on x.
Well, so yes, I guess so, right? So you apply your operator h0 times the cap psi, or you think of psi of x, and then what you get if you apply, this operator with x, you get the new function which is f of x times psi of x. It's like a diagonal of the multiplication operator, if you want. Right?
X is like the coordinates.
Yes. Yeah, that's right. Yes.
It's not like a
values.
Yeah.
Coordinates.
So, when you say Schrödinger operating on the Grecian manifold, you mean you're looking at MG as a Hilbert space?
Yes. That's right.
Why do you write it as Rn and not as Cn?
Well, I guess your Riemannian manifold is one thing, but then the domain of my operator is a different thing, right? So okay, I guess I'm saying that it acts on the Hessian manifold, but really it acts on sort of, let's say, smooth compactly supported functions on the Hessian manifold.
And when you change the metric, are you essentially changing the inner product?
Yes, that's right. So we're considering the inner product with respect to this metric. Yeah, that's right.
So, especially when you change the inner product, the operators that are considered observables, the definition of the things, right?
Mhm.
So, so when you define this H on this NG, it is supposed to be self-dual on NG.
It's supposed to be self-adjoint on NG. Yes, it's going to be essentially self-adjoint on. But you have to take, so there's some domain issues here. You have to take some Friedrichs extension of this and so on. It's a little bit. You have to be, but you can make this work. Yes, like there exists an extension of this operator. So I like to think about this operator as working on compact functions. It's compact smooth function that works nice. But there exists an extension of the operator that is
Extension you mean sort of similarity transformation which will make itself conjugate on itself dual on MG?
Well, not on MG again, like on a Hilbert space defined over MG. Yeah.
But although, yeah, there's the spectral gap and I guess won't change anything.
If you do what kind of transformation?
In the sense that you want H to be circular on MG. So right now your H is your Schrödinger operator is Hermitian.
Yes.
But if you change the inner product, the corresponding operator that will be self-conjugate on MG would not be Hermitian, it would be pseudo.
Okay.
So when you normally do that by doing a similarity transformation
Okay.
to make it self-conjugate on a different matrix. But I think everything is possible because the spectrum doesn't change.
Right. Okay. Okay. Yeah, I think operationally there are some questions about what this operator exactly means and so on. And I guess you have to redefine things like Born's rule on sort of Hessian manifolds and so on. But I'm going to try to sweep it under the carpet. Okay. Any more questions? Okay. If not, so okay, there's that example, right? The quadratic, and then we just did the same sort of thing. Like let's see what if now we take a more general function. Okay. And so again we show that self-concordance is key. And it's actually even much more key than in the first order setting. In the first order setting, I think maybe this is also a question, you can probably relax that notion. But here it seems really key because you're really sort of right, like your quadratic approximation or your harmonic approximation of H will be an approximation both, and you take the quadratic approximation of F, but you're also going to take sort of the normal Laplacian instead of the Laplace-Beltrami operator. So you need some sort of stability of that Laplace-Beltrami operator. And that's again where self-concordance is like really seems to be like the key technique to make all these like asymptotic statements non-asymptotic. So we show essentially the same statement except that there's no condition numbers now, right? So we get if there exists overall such self-concordant functions F, we can choose some gamma that's at least some polynomial, such that the ground state energy will be gamma times this spectral gap will be gamma times after some lower order corrections. And this again statement about this semiclassical operator where we sort of scale F with gamma squared. Okay. Good. So this is mostly a mathematical statement if you want. We go on to show that once you have these statements about spectral gaps, it's like you can actually think, why do we care about this spectral gap? Right? We'll study it clearly, but we're doing algorithms, or maybe some of them, and why do we care about it? So we go on to define algorithms based on these operators. Okay? And we're originally inspired also this idea of self-concordance, and so on really comes from this sort of interior point methods. Okay? So interior point methods are a way of dealing with constrained convex optimization. Okay? So we don't just want to minimize some smooth convex function F, we want to minimize it constrained to some convex subset. Okay? Like you're solving a linear program, for instance. You get a situation like that, right, where it's already constrained with some kind of thing there. I want to minimize this function, subject to X being in this convex subset. And then all of a sudden your gradient descent fails. Okay? Once you get close to the boundary and so on, your gradients are no longer defined, or you're going to jump outside of your region and so on. So what do we do? Okay, and interior point methods is really sort of like the first idea we'd probably come up with, which is let's just sort of instead of imposing this like externally, let's make it internal to the function, right? Let's introduce a barrier function. Right, let's just introduce an extra function h that blows up as I approach the boundary. Okay, so that somehow my optimization problem will sort of stay away from the boundary. Okay, so you won't jump out of the feasible region. But of course, this is a little bit tricky, right? Because also you know that, let's say if this were a linear function, for instance, then your optimizer will also always be in a corner of your convex region. So you want to be close to the boundary, right? But then you're putting this barrier function here. So it's a little bit like subtle, but you can make things work actually. And the key idea of interior point methods is, right, so you introduce this barrier function h.
Does H not be continued?
Sorry?
Why H to be continued? So this is the derivative of the
Yeah, because I'm going to solve like this problem, and I want this still to be smooth and convex. You want to have a nice barrier function. Good. So once we introduce the barrier function, we have this new function here, just the sum of.
But within the interior, you don't want the function to change, right? So it should better be zero within the domain or not required.
No. So H can be okay. I want it to be convex, let's say, and smooth. But yes, that's going to change my minimizer. But intuitively, if I take this function, I'm going to optimize it. Right, very similar to similar to semiclassical analysis. Like if I make this parameter big, then I'm going to make my barrier sort of less important, I'm going to sort of push my minimizer closer. And in fact, this is also the whole idea of interior point methods, or this sort of strategy of it's called path following, which is where you're going to solve this problem for increasing values of mu, right? And if you define the x mu as sort of the minimizer of like, let's call this function f mu.
I don't want to. I can keep on forward.
If we call this function f mu of x, we look at its minimizer, and somehow if mu is 0, will just be sort of the minimizer of our barrier. You can think about it as being like in sort of a central point inside the region or something like that. But then as mu increases, the function becomes much more important, and we're going to get closer and closer to the optimum of the original unconstrained, right? So I'm going to sort of, as mu increases, the minimizer of this function converges to the actual minimizer. Okay? So that's sort of intuitively true, right? You can make that more formal. And this also suggests a strategy, which is the following. So let's say maybe you can solve this problem for mu is equal 0, right? Because h of x somehow doesn't depend on the input, doesn't depend on f, right? So it's central point in your feasible region. Then what we can do is you can sort of iteratively increase mu a little bit, and then go from the point we were at sort of. So you're going to sort of try to like follow this path, right, for sort of discrete increasing values of mu, ultimately to get sort of close to this x star. Okay, that's what we call path following. And the way people solve it is using this Newton steps or Newton method to solve these intermediate optimization problems. So maybe this ties a little bit to the sort of technicality that I mentioned earlier, where Newton method works very well if you have a point that's already somewhat close to the optimizer. So you have like this like W exponential convergence, right? And so here by ensuring that your update, so you do multiplicative updates, but if you choose them not too big, typically this is going to be something of the form 1 + 1 over n, something like that. Then your points will not move too much, like your minimizer won't move too much, and your Newton method works well. Okay. So that's sort of key here. And that's the idea of transparent interior point methods, right? So it's a way of solving constrained convex optimization where you introduce a barrier function and you do path following using Newton's method. Okay. Is this okay? Is there any questions about this? Okay, if not, then I'm gonna move to quantum interior point methods, right? So there's been a lot of them. We're introducing one here based on the sort of ideas that we developed about spectral gaps and whatnot. And if you do quantum algorithms, like the approach is kind of natural. So we again take this maybe call it a self-concordant Schrödinger operator because okay, actually maybe I didn't put this on the last slide. So these IPMs work best if your barrier is a self-concordant function. Okay? There's a lot of like study about which barrier functions are self-concordant. We have a very good understanding of which these are. So this is a context where self-concordance, I guess maybe it doesn't pop up naturally, but at least it seems to be the way to constrain, like to choose your barrier functions. Choose your barrier.
So F and H are now both semi.
No, so F, if you want to think about F as maybe a linear function, like C transpose X or something, actually you can reduce any convex optimization problem to one where F is just a linear function. But that H has to be a self-concordant barrier. So H blows up around the barrier, around the boundary of the feasible region. So we define this. And then for different mu's, thank you. For different mu's, we get sort of the central path again, right? Because you get these ground states, psi mu. And as mu increases, these ground states are going to sort of concentrate around the minimizer of this. So you imagine instead of having these points, you sort of these quantum states that you can drag along this path. And they have a corresponding gap delta mu. And that's sort of what we worked on, right? We already analyzed what this gap is. And in fact, we also showed that the ground state will be close to that of the harmonic approximation, so it'll be close to the Gaussian. So we have these Hamiltonians, and we have these Gaussian ground states that live and sort of concentrate on the central path. Now, yes.
How do you simulate this Hamiltonian with this direct edge?
So, I mean, how do you simulate this Hamiltonian is even without this barrier function, a bit of a question, right? So, it really depends on the setting. And so here we're really just trying to make arguments about, like, let's say, you have access to this Hamiltonian, you can simulate it, then what kind of algorithms can you derive from that? Then the question, how you're going to simulate that is a very valid one. It's a bit of an open question that was sort of a future work question. But maybe what helps here is that really, like, applying this operator, at least intuitively, like, this part should just be like zero order information. Like, it should just depend on like the value of H and value of F. And H is going to be an explicitly defined barrier function, right? So that should not be different from class. This operator, if this is a primary operator, should, like, at least intuitively, depend on second order information, right? So if you're going to like discretize your Hamiltonian simulation, then probably you want to say, okay, what if I have, sort of queries to these functions and queries to hash these functions? And then I'm sure you can find classical Hamiltonian simulation. But it's it'll be tricky, and it's kind of a nice open question, but we're sort of, taking the liberty of
Is it classically Hamiltonian simulation?
I mean, really classic. Yeah. And again, like, all these things have sort of analogies in classical algorithms as well. You have things like Hamiltonian Monte Carlo, where you're doing you're using a classical Hamiltonian dynamics, where also you're going to assume, like, first you assume you can integrate this exactly, and then you have Hamiltonians that depend on second order information and so on. And then, later papers sort of discretize and stuff and so on. So there's really sort of a lot of like precursors to these ideas. Good, so we define this, and then like the idea is kind of natural of what you want to do, right? You want to sort of like take this state, start here, and sort of drag it to the minimizer. So what we prove, we prove rigorously something, but making assumptions, that are definitely like up for debate. Right? We're just saying that if you can do that, let's say we reduce the problem to doing these. So if you assume like that you can prepare the initial state or an approximation of the initial state. Right? So this is going to be a Gaussian around like some center of the feasible region. Right? Again, this will be independent of F if you phrase things correctly. So you could say that this is like input independent in some settings. Then some technicality, we assume that you have essence of the ground state energies. But this can be expressed. You have expressions for this based on the Hessian function value of the minimizer. So these are not like sort of alien objects. So we understand what they are. And finally, right, this is like the point where we assume that you can do Hamiltonian simulation, in fact, you control simulations. If you can do these things, then we prove this theorem. So starting from this initial state or approximation of the initial state, we can prepare psi mu for mu large enough so that we're really concentrated around the minimizer. So we're preparing this quantum state concentrated around the minimizer while evolving the Hamiltonian mu. So by applying this operator a number of times, that's polynomial in dimension and log one groups. Okay.
So this should be exponentially better than classical in terms of 1 over epsilon. Classically also you get this stuff.
Yeah. I mean, I guess you could even get doubly exponential. We have like non quantities. No, so we're not comparing like I think one point you could try to make is that okay, we're sort of solving it different. We're sort of solving a quantum optimization problem, right? So this is something I want to understand. Like now, we have these like classical functions, but I'm sure there are sort of like quantum operators that we actually want to optimize. We don't have a classical analogy. But in this area of convex optimization, I guess we're not expecting big speedups because we're already classical elements. So it's more sort of the conceptual.
And I guess this is where you can just use this word strategy.
So let me get to that. So how do we prove this theorem? Okay, maybe just stress. So this is compared to if you can do the same algorithm with the Euclidean Hamiltonian, right, where you just take the normal Laplace operator, and then you get this condition number showing up. But this is then the maximum condition number of all the Hessians that you encounter, like along your central path. But sort of the key point is that as you take mu to be large, like you're going to be extremely curved, like you're going to get super close to the boundary, and your Hessian gets like highly ill conditioned, right? So this is really sort of a game breaker for a lot of, and in fact, a lot of the existing quantum theory point methods, they all have this thing showing up. There's no classical algorithms that would like so tolerate that. That thing is going to blow up, and we don't have a good hold of that. So we don't want that. So here we show that okay, if you use the sort of second order information, we're using more. It's that I mean, then we'll be clear we're using second order information. And then you can get rid of that condition. But so what's the idea? Maybe I should tell you that probably like the simplest idea would be it's an online question maybe.
Yeah, there is a question mark. Ask them to speak up.
Hi.
Hi.
So, I think it's like some kind of like efficient method to prepare the ground state of some class of Hamiltonian, right? So, do we know anything about like classical hardness of like ground state preparation of like such Hamiltonians?
Classical hardness of preparing. How would you define the classical hardness? Do you mean for estimating the ground state energy or something?
Yeah. So I think like this theorem like gives you some method of preparing ground state, right, for like these kind of Hamiltonians. So
Yeah, that's right.
do we know if like these kind of Hamiltonian are like ground state of these Hamiltonians are like hard to prepare classically, or like do we know anything about it?
Oh, okay. Yeah, so I think there's some recent work about complexity of Schrödinger operators, which has I think they prove some sort of I think these operators are essentially stochastic. So I think they tie them to maybe stock MA or things like that. So there's some nice work on that. But yeah, I think in this setting, like your F is is the classical, convex function, right? We can optimize it. So, I guess you could just apply or prove and say that the ground states of these things are Gaussian centered around the classical minimizer. So I guess there would not be a lot of complexity in that case.
Okay, I see. Thank you.
Okay. Yeah, thanks for the question. Good. So in the last minutes, maybe I'll go through the key ideas a little bit. So a very natural approach would be to do adiabatic algorithm, right? Because we're sort of changing a parameter continuously, and we also sort of drag along the ground state, and we have the spectral gaps. We have everything, so we figure we're done. But then there don't really seem to be good adiabatic algorithms that work for unbounded Hamiltonians. And again, the statement is sort of half true because we do have asymptotic statements about that, but we don't have non-asymptotic statements, right? And so we try to come up with a different way of doing it, which is a bit of like both ideas. So what we do is we do quantum annealing, which is more of a discrete type algorithm. We make discrete jumps from one quantum state to the other, and we know that we can do that efficiently if these quantum states have good overlap, and we can reflect around these quantum states. Okay, so if you can do that, then you can go from psi mu0 to psi mu t in some time, something like time, like with t log 1 graph some calls to these reflections, something like that. It's kind of a relatively standard technique. And then we use our semi-classical analysis because that tells us that, for each of these ground states, we have Hamiltonians of which we know what spectral gap is. And for which we know that these states are going to be approximately Gaussian. So that this allows us to prove that there's good overlap, right? If we don't change mu too much, it puts a constraint on how much we change mu. And the spectral gap here, we're going to use that to do this reflection, okay? Because very naively here, what would we do, right? If we do this reflection and we're given a Hamiltonian with a spectral gap, we would do quantum phase estimation, right? So if you can do controlled Hamiltonian evolution, then you can do quantum phase estimation on this operator where the complexity scaling is 1 over the gap, and then you're done. You can do the reflection. The problem here is that this operator is unbounded. Okay, so H, the operator of H is unbounded. Right, the energy levels of H go to infinity, and so we get sort of aliasing problems, right? Like you typically want to imagine in quantum phase estimation that all your eigenvalues lie on the unit circle, but now they're actually going to wrap around like, a different number of times. And if you want to sort of learn something about small eigenvalues, it's not even well defined once you wrap things around the circle, right? So you get like sort of like ghosts showing up from higher energies and so on. And we didn't really manage to make that work. So okay, we did something else. And I think this new trick is based on the Haber-Shatonovich transform. So this is something that with Chantal actually we used at some point. So I was very happy to revisit that. There we didn't use it in like a continuous setting. So we actually did the work to discretize stuff and so on because we didn't want things. But here we have something continuous. And the key idea is, so very roughly, because running out of time, so very roughly it tells you that it's sort of linear combination of unitaries, but on a continuous register. So let's unpack this. So this is our main state. This is the main state of where H mu acts on. And then we take this extra register where we put a Gaussian state. So it's like a continuous variable register. This depends like a quantum harmonic oscillator if you want. The graph of a quantum harmonic oscillator. And then we're going to apply our Hamiltonian. But instead of just H, we do H stands for X hat. So what does this really mean? It just means that it's going to look at what the value is inside the register and condition of that. It's going to apply the operator that many times. Okay? So this is really LC, if you're familiar with that, right? So this would be like your control register, you put it on a Gaussian, and then this operator will sort of apply that operator, so Gaussian, and go ahead and say how we find that. And then you have to sort of do some post-selection, right? Like if you then sort of post-select and getting again a Gaussian in that register, then through this Haber-Shatonovich transform, you get the following object, which seems weird. But this is essentially an imaginary time evolution of your H3 operator. So we don't have an I here. right? We get a minus something. And if you assume for a second that the ground state energy of H mu is 0, then this thing here kills all the non-zero eigenvalues, right? If you take t to be sufficiently large, and this is where the gap comes in, right? You need to take t to be at least 1 over the gap. And this is going to kill all the larger eigenvalues, except the 0 eigenvalues. So essentially, this thing is a projector onto the ground state energy. Okay? But this entire thing is not unitary because I did this post selection. But the key point is that we just need to do reflection, right? So what we're going to do is we're going to sort of start from this state by this operator and condition on this Gaussian state, like flip the sign, and then undo the thing. Right, so you get sort of reduced reflections to doing projections.
And it doesn't like make me worry about how much overlap is with that.
Guaranteed high overlap.
Well, no, but also we don't care about that because we just do we want to do reflection, right? So if I have small overlap, I don't care about it.
But I think somehow it can keep it from confident because the success of the algorithm somehow is conditional.
No. So the reflection does depend on that. Like this entire procedure, I could put the phi here because it makes it a bit clear, but you can drop the phi, right? And so you can say that this operator here is just a projector onto phi mu. So that allows me to implement this reflection based on psi mu on any state. Sort of how well I'm approximating just depends on t. But of course, I agree. Like you want to do amplitude amplification, and there, the overlap matters.
It's saying the reflection won't come.
All right, I see what you mean. So I think there's a mismatch of length. I think what he's talking about is just this. What you're talking about is this plus amplitude amplification to actually amplify and get like something like the projected state.
Okay, I don't following too well.
Okay. But anyway, so I think this sort of strategy also encourages us a little bit to we're a bit more convinced that doing things on continuous variable system and not discretizing stuff or just directly working on the but it gives new ideas and you can make things work in a non-trivial way. So yeah, we're sort of okay for that. Good. So I'm going to wrap up. So the summary is that we do the semi-classical, there's non-asymptotic semi-classical analysis of first order, second order Schrödinger operators. And we introduced, it's based on that, we introduced continuous variable quantum interior point method. Both of these are independent of condition numbers, right? Sort of intrinsically using second order information. Some open questions. So you mentioned a lot in our paper, which I guess should be out at least before 10th of October. We're proving spectral gap bounds for convex potentials by sort of localizing stuff around the minimizer. But really, convex functions are already very nicely behaved. So there should be more global ways of proving these spectral gap bounds. And then finally, there's this question of discretization. So I think it's a nice question that can we do Hamilton installation in this sort of current space time? Right? Like can we give you first order and second order information? I'm pretty sure you can do some sort of trotterization, where you just use the local hash and something like that. But yeah, that remains to be looked into. So I'll stop here. Thank you.